Good morning, I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next part of Unit 3rd, that is related to noise analysis of different types of systems, different types of receivers, of amplitude modulation, FM modulation, different types of systems we are going to study. So, first we will discuss what is noise. So, noise is basically a disturbance or an unwanted signal that is random in nature and interferes with the desired signal. So, basically where noise will going to affect the signal, it can be internal to the system, it can be external to the system, that is two kinds of noise that we are going to study. So, if the level of noise is much larger than the signal, then the reception becomes unreliable, which means at the receiver side when we are going to receive the signal, when we received the signal, when we want to demodulate the signal, then the good quality of the signal will not be reviewed. So, the noise occur in the form of audible bliss or crackle at the output of an audio amplifier. So, there are different types of noises in different applications, like in case of when we are talking about speaker noise, then there will be a loud sound will be there, hiss sound or a crackle sound will be there in case of audio amplifier. When we are talking about images, then the quality of the image that we receive is not good, it will be affected with different types of noise like salt pepper noise or flicker noise or different types of noises will be there, which will going to reduce the visibility quality of the particular system. Next is when we are talking about signals, then in case of signal it can be continuous time signal, it can be discrete signal. In discrete signal, when number of bits are changed at the receiver side, let us say I have transmitted 8 bits, I have received 7 bits or received 8 bits only, but 1 bit or 2 bit will be changed its value, like from 0 to 1 it will be changed from 1 to 0. So, 1 or 0. So, that is the effect of noise. So, in case of video amplifier, noise has snow like appearance on TV screen when the TV set is tuned to a weak station. So, that is the concept of noise. Now, noise can be of two different types, like external noise and internal noise. External noise is man-made and natural noise. In case of man-made, it will be an industrial noise. Natural noise is atmospheric and extraterrestrial noise. So, extraterrestrial, when it is due to sun, it will be known as solar noise. When it is due to stars, it is known as cosmic noise. So, these are two types of noises. Now, next is internal noise. Internal noise are basically of 5 different types, like this one is short noise, thermal noise, then there will be flicker, then partition, and transit time noise. So, this transit time noise is also known as high frequency noise, this flicker noise is known as low frequency noise, because its power spectral density is inversely proportional to the frequency. So, that is the case of internal noise. So, these are the different types of noises that will going to affect the quality of the signal that a user will receive. So, now we are going to discuss the analysis part, where we are going to derive and parameter that is known as figure of merit. Now, this figure of merit is related to signal to noise ratio calculation. So, whatever receiver we are considering, whether it is DSP-SC receiver, whether it is AM, whether it is FM, we have to consider the signal to noise ratio at the receiver input and signal to noise ratio at the receiver output. Now, by considering these two values, we can find out figure of merit, and the inverse of figure of merit is known as noise figure. So, this figure shows the model of a DSP-SC receiver using a coherent detector. Now, what is coherent detector? Coherent detector basically means whenever we are doing modulation, we require two signals. First one is message, other one is the carrier signal. Now, carrier signal, whatever signal we have used at the transmitter side, it has to be used same at the receiver side. Like you can see, like this is the receiver model of a DSP-SC local oscillator, whatever this signal we have considered at the transmitter, it has to be same at the receiver side. Then only the signal which is received at the output will be same as what we have transmitted. So, that is the case of coherent detection or synchronous detector. So, DSP-SC signal is this one, it is passed through a band pass filter, then it is passed through a coherent detector, that is product combination of product modulator where the input will be a local oscillator, then output will be a low pass filter. So, you can find out the signal to noise ratio. Now, this is noise, this is nothing, it is the AWGN noise, that is additive white Gaussian noise. So, as shown in this figure, the filtered signal is applied to the coherent detector. It is multiplied with a locally generated sinusoidal wave, that is cos omega ct, using a product modulator. The product is then filtered using low pass filter. So, basically this is some theory that is related to the previous diagram. So, now we are going to derive the expression. The DSP-SC component is given by ST is equals to CAC cos omega CT into MT, where AC is the amplitude of the carrier signal, C is nothing, this is the system constant, system dependent scaling factor, MT is the original message signal which we want to modulate, which we want to receive at the receiver side. So, now the average power of the DSP-SC modulated signal component is given by C square AC square P upon 2. So, what is P? P is nothing, we have considered a parameter that is related to the power of this signal, that is the message signal. So, whatever signal we can consider, it can be single tone, it can be multiple tone, its power is equivalent to capital P. Now, the average noise power in the message bandwidth is denoted by W, which is equals to W into N naught. What is W? W is the bandwidth of the signal, means the input signal will be extended from minus W to W. So, that will be N naught by 2 into 2 W. So, therefore, the channel signal to noise ratio of the DSP-SC modulation system is given by SNRC, which is equals to C square AC square P upon 2 P upon 2 W into N naught. So, now let us devise the output signal to noise ratio of the system. The total signal at the input of the coherent detector is given by xt is equals to st plus nt. Now, what is st? St is nothing, it is the input signal, nt is nothing, it is the noise that we have considered. So, noise is what basically we have considered AWGN noise, when that is passed through a band pass filter, so that will become a, and that will be denoted by NT. And this is passed through a band pass filter, that will be denoted by NT. So, this will be a additive white Gaussian noise, this is passed through a band pass filter, now output will be denoted by NT. So, that is the case. Now, from the circuit, the narrow band representation of the filtered noise, that is NT, is given by this equation, that is NIT cos omega CT minus NQT sin omega CT. So, that is the representation of the noise, which consists of in phase component and quadrature phase component both. So, now we can substitute this particular equation into the previous equation, where we can find out xt, which is equals to CAC cos omega CT into MT plus NIT in minus NQT, where NIT and NQT is nothing, this is the in phase and the quadrature phase component of NT with respect to the carrier. The output of the product modulator is given by this equation, that is Vt is equals to xt into cos omega Ct. Now, this is nothing, this is the input signal xt, this one multiplied by cos omega Ct, means it is multiplied by a signal which is generated by the local oscillator. So, that will be the output of the system, that is Vt. So, we can put the value of xt over here and we can find out the equation for Vt. Now, we can when it is multiplied, when cos is multiplied by the local oscillator signal, that is again a cosine signal, then cos square theta term will appear. Now, this cos square theta can be used using a simple trigonometric formula, that is 1 plus cos 2 theta by 2, that will be used. So, cos square theta will be equals to half plus cos 2 theta by 2, and also we can find out its value, that is sin 2a is equals to sin 2 theta is equals to 2 sin theta into cos theta. So, that is another formula for sin 2 theta. So, we can put all these values, and you can see that after this whatever we have appeared, whatever values will be appeared, it will be passed through a low pass filter, and then the higher frequency terms will be filtered out, and at the output we are having only this message signal which will be having some DC terms you can see, and the noise term which is also reduced to half. The above expression we observe that the message signal component at the receiver is C AC empty by 2. Therefore, the average power of this signal will be C square AC square P by 2, that is same that what we have considered at the input side, where P is the 0 power of original message signal. Then signal to noise ratio at the output will be C square AC square P divided by 2 divided by W into N naught by 2, which means signal to noise ratio at the output. Now, from this we can calculate the figure of merit, which will be signal to noise ratio at the output upon signal to noise ratio at the input, then this will be equivalent to 1. From this we can also calculate the noise figure, which is equivalent to 1 upon figure of merit, and here since it is 1, so noise figure of DSP-SC receiver is also a unit, and it is a dimensionless quantity. Now, next is noise in AM receivers. So, in this case we will going to consider a receiver model of AM. So, as noise affects the amplitude in AM system, the signal to noise ratio is the commonly used measure of performance. So, figure third one is showing the receiver model of AM, where ST is the amplitude modulated signal. It is added with the noise, that is AWGN noise, then it is passed through RF amplifier mixer. So, this is nothing, this is a kind of super heterodyne receiver. Now, what is the aim of this super heterodyne receiver? Whatever frequency it will going to receive, it will convert to an frequency, that is intermediate frequency, and in AM its value is 455 kilohertz, that is fixed. Then it is passed through detector, and to filter out the higher frequency components, it will be passed through the low pass filter. So, that is the concept of noise in AM receivers. So, as shown in this figure, the noise generated with the receiver can be referred to as receiver noise and the antenna noise. The addition of this receiver noise and antenna noise is considered as noise receiver. So, first we will write an equation for the received signal. Since it is an AM signal, the equation will be ST is equals to AC 1 plus Ka MT cos omega Ct, where AC cos omega Ct is nothing, it is the carrier signal, MT is the message signal, and K is the constant that is related to amplitude modulation. Now, we can express the average power of this by using this particular formula, that is AC square 1 plus K square P divided by 2, where P is the average power of the original message signal, that is MT. Now, since we have calculated signal at the input of the receiver, we can also calculate the noise at the input, that is denoted by again same formula W into N naught. Then signal to noise ratio at the input will be equivalent to this formula. Now, we have to analyze this particular analysis at the receiver side of the receiver, at the receiver output. Then the output of the IF filter is Xt, and it is given by Xt is equals to St plus Nt. What is St? St is the received signal, that is the AM signal, and Nt is nothing, it is the noise, that is AWGN noise. When Wt is passed through a band pass filter, it will be equivalent to Nt. So, after substituting the value of Xt in this particular equation, the Xt equation will reduces to this form, that is AC 1 plus K into Mt cos omega Ct plus Nit cos, that is the representation of noise in phase component and quadrature phase component. So, after putting this value and multiplying it with the signal which is generated from local oscillator, we will have this term, that is AC Ka Mt cos omega Ct plus Nit cos omega Ct. So, that is the value of at the receiver side. From this equation we have to calculate the signal power and it is equivalent to AC square Ka square P upon 2, and the average power is given by W into N naught. So, signal to noise ratio at the output of this receiver will be equivalent to AC square K square P divided by 2 W into N naught. So, after since we have calculated SNR at the input and the output of the same receiver, we can find out the figure of merit. So, SNR at the output upon SNR at the input, its value will be equivalent to Ka square P divided by 1 plus Ka square P, where P is the message signal power, that is MT, and Ka is an constant that is related to amplitude modulation, and P, since we are considering MT as AM cos omega MT, which is nothing, which is a single tone modulation. Single tone signal means only one frequency component is present in the message signal. It can be extended to more than one also, maybe 2 frequency components are present or 3 components are present. So, that is a message signal. From here we can calculate the power, that is equivalent to AM square, that is mean square value of this MT, which will be equivalent to AM square upon 2. And when we consider a resistance in the circuit, then it will be equivalent to AM square upon 2 R, and if it is not given, then we can also we can consider it as 1 ohm also. So, that is the value of P. So, after putting all these values, it will be reduced to mu square upon 2 plus mu square, where mu is nothing, it is the its value is equivalent to Ka into AM. Now, what is AM? AM is the amplitude of the message signal and Ka is the proportionality constant. So, that is signal to noise ratio or figure of merit for amplitude AM receiver. So, this is all about today's lecture. Thank you.